Hi students, welcome to the session on inductor and inductance. Right, first we see what is inductor. Inductor is a component which stores energy, right? Stores energy in its magnetic field, whereas capacitor is a component which stores energy in electric field. Hope you know that, right? So inductor is like a coil of fire. So it's a symbol of inductor. It's like a coil of wire, right? So we have already known that when current flows through a circuit conductor, it will create a rotating magnetic field, right? So this we studied as per Ampere circuit law or by its Savart law, right? When it is a single conductor, when you have a more number of turns, it will create more magnetic field, right? What is happening there is, if we have a right, so if you have a more turns, what happens is it will create right, when current flows through this more number of coils, it will develop a strong magnetic field like this. Okay, it will be having a strong magnetic field. Fine. Okay, this is what this will be having strong magnetic field. It will be going like this. So clear. So more current flowing through this, since it is having more turns, more magnetic field will be produced. So when current starts flowing through the coil, the energy develops in magnetic field and reaches saturation. So energy reaches saturation. When current flows through a coil is made to become zero, what will happen is the magnetic field collapses and the energy will become electrical energy, right? So this is what about inductor we must know. Now we learn about inductance, right? So what is inductance? We know that when current flowing through a uh, conductor, it will produce a magnetic field, because as per Ampere circuit law, H dot dl is equal to I. So I produces H. H leads to B. B is equal to mu H, we know. This implies this will lead to flux. What is that flux? That is nothing but B dot ds. So what is the thing we learn from here? When current flow through a coil inductance increases, so coil increases, the flux will also increase. Right? That is the thing we learned here. Okay. Now this flux is the reason for allowing current. This flux only allows current to pass through the each turn of coil. Right? This flux allows current to pass through each turn of coil. If our coil has n turns, then the flux links the current n times. Okay, so n times means n turns means n times. That's well known. So that flux linkage is represented by the symbol lambda, that is given by n phi. For one coil, one flux; for n coil, n phi flux. This lambda is known as flux linkage. Okay, so we know that when current increases, when I increases, pi increases. When pi increases, lambda will increase. So that will give lambda is equal to n phi. So when current increases, lambda will increase. So what is the relationship between lambda and I? Lambda is directly proportional to I. That proportionality constant is known as inductance. So that constant is known as inductance. That is given by lambda by I. Lambda is equal to n phi by I. So L is equal to n phi by I, where n phi is known as flux linkage that we know, or magnetic flux. See, n phi is just a flux. So magnetic flux per current. That's what we know as inductance. Okay, inductance is represented by the symbol L. We know, as per Faraday's law of electromagnetic induction, whenever flux linking with the coil changes, what is that flux linkage? Lambda. When lambda changes with respect to time, the EMF will be induced. This is what Faraday's law of induction, right? So here you see that minus indicates opposition. The induced EMF opposes the cause. So what is that? Induced EMF oppose. Oppose what? Oppose what? Change in current. Why lambda? We know that lambda is given by minus d by dt. Lambda is equal to n phi. From this equation, n phi is equal to Li. N phi is equal to Li. So you bring outside minus L is a constant. You take it outside, d by dt I only. So what is that thing? We write here. From here we write V EMF is equal to minus L di by dt. Right? Instead of n phi, you substitute Li. L is a constant. Take it outside. So it is minus di by dt. Okay, because this gives n phi is equal to ni. Okay, now from this we can say that induced EMF oppose change of current or time varying current. The current varies with respect to time. So what is that opposition quantity? That opposition quantity is known as L. So who is opposing? L opposes the change of time varying current. What is L opposes the time varying current? What is time varying current? Time varying current is nothing but our AC. So inductance opposes AC. That's what we have to know. Inductance blocks AC, allows DC. Simply we can quantify L as opposition to the change. Okay, I write change in a different way. Opposition to the change in the current. What is resistance? Resistance is the opposition to the current. That is very important. Opposition to the current, whether it is time varying current or steady state current. But inductance opposes only time varying current. You see, current varies with respect to time. So who is called time varying current? AC. Steady state current is known as DC. Resistance opposes both time varying and steady state. Whereas inductance opposes only time varying current. That's what inductor blocks the AC and allows DC. So what is inductance? It is the opposition to the change in current. Now we define self-inductance. That is simple. It must also be a opposition to the current. In what way? Let us see. It is ability of the circuit to resist, as usual, you see, resistance has come, to resist any change of flux which is produced by time varying current. Who is producing the flux? Time varying current. We know current will produce flux. This current is produced by the time varying current through the circuit. That's what your self-inductance is about. So I hope understand the concept clearly. If you have any doubt, please ask me in comment section. I will clarify all your doubts. Thank you.